This is a short set of slides that will finish the unit on the mole unit, and when you're done with this, you should be able to do all of homework 4. I'm going to have a Zoom session the day homework 4 is due, and I can give you some additional problems or just help you work on homework 4. Anyway, this is some additional calculations from formulas. We're going to look at the percent composition of a substance based on the formula, and also how to determine the formula from data, because empirical literally means from data. This is a pretty short set of slides, so I can probably get through this in one video. So let's go ahead and get started on this. All right. So remember that a formula is good for any amount of the substance. So a formula is good for 1 molecule of a substance. It's good for a mole. It's good for 74 tons. It doesn't matter how much. The formula is always good. A pure substance always has the same composition. So just to remind you, 1 molecule of P2O5 has 2 P atoms and 5 oxygen atoms. A mole of P2O5 has 2 moles of P, 5 moles of O. So see the ratio 2 to 1, 5 to 1. Is the same. And then, of course, Avogadro's number for a mole and the molar mass. All right, we did this on the last set of slides. So the law of definite composition says that a pure substance always has the same percent composition by mass. And percent composition is the percent by mass of each element in a compound, and you can calculate it from the formula. And you just want to be looking how the question is worded. So if a question says, just ask you for percent of one of the elements, you don't have to do the whole thing. You could just do it for that element. So just to go through an example, if we were to calculate the percent composition for C5H10O5, the percent carbon would be the mass of the, percentage is always the part over the whole times 100. So the mass of the carbon over the mass of the compound times 100. The percent hydrogen would be the mass of the hydrogen divided by the mass of the whole thing times 100. And the percent oxygen would be the mass of the oxygen or the mass of the whole thing times 100. But the problem is that we don't have any of those numbers. And this is enough information to solve the problem. So how do we get those numbers? Well, since it doesn't matter how much of the compound we have, right, the percent composition is always going to be the same. If we do it for a mole, we know the mass of that compound, right? Because the mass of the compound is the molar mass. So to calculate the molar mass, just as a review, we have carbon, hydrogen, and oxygen. From the formula, there's 5 carbons, 10 hydrogens, and 5 oxygens, right? And then we use the molar mass of each, and then we add them up. And so the whole thing, the molar mass, is 150.16. And in addition, we have the mass of the carbon, the mass of the hydrogen, and the mass of the oxygen. So if we go over to the right here, the percent carbon is going to be the mass of the carbon, just like we did saw in the last slide. And so from over here, the mass of the carbon is the 60, and the mass of the whole thing is the 150 times 100, so it's 39.99% carbon. On something like this, by the way, as far as significant figures, just give me 2 decimal places. All right, the mass of the hydrogen, similarly, is going to be the mass of the percent hydrogen, be the mass of the hydrogen over the mass of the whole thing. All right, and so the hydrogen is 10.10 and the whole thing, so 6.73% hydrogen. And then lastly, the percent oxygen, right, just like on the previous slide. And so taking the numbers from over here on the left, the 80 over the whole thing times 153.28%. That's how you calculate them. And you'll note that the percentages do add up to 100%. And they should. Now, it's very tempting on a problem like this to calculate, say, the carbon and the hydrogen and get the oxygen by subtraction from 100. And you certainly could do that, but it's not a good idea. And this is why. If you made a mistake on one of these, you would have this one wrong as well. It's very rare in problem solving that you have a way to check your answer. So when you do have a way to check your answer, it's not a good idea to throw it away. So it's smarter, just being a good problem solver, to calculate each one separately and then add up to make sure they do indeed add up to 100%. And they'll add up to 99.8, 100.02, something like that. They should be very close to 100. It's just rounding. All right, so that's percent composition. The other one is calculation of an empirical formula. That's the other type of problem we're going to do here. The last set of material that's on homework 4. And again, experiment 5 in the lab is going to go over this as well. You would actually do this in the lab. So remember, an empirical formula has all of the elements in the lowest whole number ratio. All right, so it has to be a whole number ratio because remember, formulas have to be whole numbers. There's no such thing as a fractional amount because the formula is good for one molecule. So the formula number is a mole ratio, and again, formula is good no matter how much other compound you have. So it's easiest to do this. Well, let me go through the steps. So the steps are determine the moles of each element, divide each number of moles by the smallest. That makes the smallest a 1. That gets us to a whole number. Often there's only 2 steps. Often that it just falls right out. If you get a fraction, this would be the F necessary, you look at your fraction and then you multiply each number of moles by some whole number to get whole numbers. And I know this doesn't make sense, but I'm going to do an example. Right? So the example is here. The compound is 69.94% iron by mass, and the rest is oxygen. Let's determine the empirical formula. So we know it's going to be FeXOY because it's iron and oxygen. Just a little by the way, how do we know which element we write first? If you look at the periodic table, whatever is either further to the left or lower down is written first. Why? Because that's an agreed upon convention. Now we know since the rest is oxygen, that there's 30.06% oxygen. Now, if you remember, going back, the first step is to get the moles, because the formula, these are going to be moles. How do we get the moles when we have percentages? Well, remember, the formula is good no matter how much of the compound. So if I had 100 grams of the compound, I would have 69.94 grams of oxygen, 30.06. You could pick whatever amount you want. You could say 16.5 grams of the compound, but then you'd have to take 16.5 grams times 69.94%. So make your life easy. Use an easy number. Or you can make it for 1 gram and make it 0.6994. All right, so let me go through the steps. All right, the first step, so these numbers correspond to that previous slide. Determine the moles of each element. So we've done a whole bunch of that. So in the compound, we have 69.94 grams of iron. We use the molar mass, so there's 1.252 moles of iron. And for the oxygen, similarly, 1.879 moles of oxygen. So if we stopped here, the formula would be Fe 1.252 O 1.879. And that is the correct ratio, but we can't have fractional. So what we do, the trick is, remember it's a ratio, so if you remember algebraically, so I told you what the steps are, I'm going to tell you the why. So if you remember algebraically, you can multiply or divide these two numbers by any number you want, as long as you multiply or divide them by the same number, and the ratio will stay the same. So step 2 says we look at the smallest number, divide each of them by that smallest number. That way this becomes a whole number. So step 2, divide each number of moles by the smallest. So from the previous slide, the iron was 1.252, the smallest was the 1.252, the oxygen was 1.879. We divide them each by 1.252, and we get 1 and 1.5. So the formula would be FeO 1.5. Now, like I said, frequently you come and you get 1 and 1.99, or 1 and, I don't know, something that's very close to whole numbers. But in this case, we did not. This is an example that has a third step. So what we do is you look at the fractional number and you say, well, what whole number? You don't want to use a fraction because then you get a fraction here. What whole number can you multiply 1.5 by to get a whole number? Well, we all know 1.5 times 2 is 3, right? Just remember things like 0.25 is a fourth, those types of stuff. So if we multiply this one by 2, we have to multiply this one by 2. So if we multiply each of them by 2, right, the 1 times 2 is 2, the 1.5 times 2 is 3. That means our formula is Fe2O3. So I'm only doing the one example. There's some in the book, and the homework has some problems like this, and I can do some during Zoom sessions if you want. On the Zoom, the synchronous meeting on the Zoom session, I'll make up a couple more problems like this if you want me to, or I can just go through homework 4. That is it for this. I told you this was a relatively short set of slides. That's this material. So you now have enough material to do homework 4, and I'll see you on Zoom sessions.